All right, here's an example of the type of question that you might see for learning objective 3. I actually chose this problem because I felt like it had the foundation of how you would solve this problem was aligned with my expectations of things that you would know to do in this specific situation. And so I thought this would be a good way for you to see, I think you should know this, and this is how we would solve this problem. So here's the problem. I have a deuteron, which is the nucleus of an isotope of hydrogen. It basically means it has an extra neutron in the nucleus, and we're given the mass of it, and it has a charge of +1, plus equal to the charge of an electron. And it's traveling in a circular path with a radius of 6.96 millimeters in a magnetic field with magnitude 2.5 Tesla. This was a special example of motion that we talked about in class, where you had some uniform magnetic field and the object enters into it and it starts going in a circle. Okay, so one of the things that we talked about when we looked at that type of motion was that it would have, we were looking at F equals ma, but the acceleration of an object in a circle is centripetal acceleration. So that was sort of the basis of understanding the motion. Now, the force that charged particle feels is the force that a particle feels when it moves into a magnetic field. And in this scenario, which we have been told, the velocity vector and the magnetic field vectors are perpendicular to each other. So the force that this charged deuteron feels is simply QVB. And that's the force, and we're going to set it equal to the centripetal force, or the mass times the centripetal acceleration. And this is the basis of this type of motion. So I want you to really be familiar with this expression and be able to manipulate it to find values that you're asked to find. For instance, in this problem, you're asked to find the speed of the deuteron. So you want to solve for v. If I solve for v, as I rearrange it, I'm going to get Q, B, R over M is equal to my velocity. And so that's pretty simple. Then I know the charge. It's the charge of an electron or a proton, but it's positive because it's positively charged. The magnetic field, we're told, is 2.5. The radius is 6.96 millimeters, so I change that to meters. And then the mass, we're told, is 3.34 times 10 to the minus 27 kilograms. And so altogether, I get a speed of 8.34 times 10 to the fifth, and that's in meters per second. Now, that's a perfectly reasonable speed. We always want to try to avoid going faster than the speed of light, which the speed of light is 2.99 times 10 to the 8th meters per second. So when you get a speed that's bigger than that, you have a problem. You didn't do it right. Now, the second part of this, so this was part A. Part B is asked for how long it takes to go half a revolution. And that makes me think of the period. The period is the time for one revolution. And the way that we could think of finding the period is we'd go, well, the time is going to be equal to how far it goes, which would be 2 pi r, divided by the speed, which is v. So that is how I find the period. I could calculate that period and then take half of it because it's only going halfway, or I could just kind of take a shortcut and go, oh, well, the time I'm looking for is it's going halfway around the circle, which is just pi times the radius, and then divide by my velocity. And that'll give me my time straight up. But again, this is sort of a relationship that I would like you to be familiar with, like how do we define the period and how we would relate that to this circular motion. So we've got pi times the 6.96 times 10 to the minus third. I'm going to use the velocity that I found in the first part. And my time ends up to be 2.62 times 10 to the minus 8 seconds. You might be like, wow, that's really small, but kind of looking at the numbers I have, the radius of this path is pretty small. It's measured in millimeters, and the thing is going pretty darn fast. So I'm like, seems okay. Now the last thing is, what is the potential difference would the deuteron have to be accelerated to acquire this speed? This is another relationship we've seen a couple times and it's been useful to you. So hopefully you remember that when it goes through a potential difference, it has a change in potential energy equal to Q delta V. And this results in a change in kinetic energy. And so I'm going to assume it starts from rest and its final velocity is the speed that I saw right here. And so this is the relationship that's going to help me find the potential difference. The delta V is going to be 1/2 mv final squared divided by the Q. So the mass is 3.34 times 10 to the minus 27. My velocity is 8.34 times 10 to the 5th squared. And then I get 2 times this charge. And I get a potential difference of 7,360 volts. So I hope you find this helpful, this example. There are definitely things in here that for this LO that I hope that you're familiar with. Obviously, this wasn't a problem on torque, which is another possibility, but this was a nice problem for force.